I just came back from the Beijing Olympics, and we saw some really fast swimmers there, and their reaction times jumping off the blocks averaged between 0.6 and 0.7 seconds, and we thought that was pretty fast. We want to see if we can do it ourselves. So we're going to drop a ruler, and after 5 benchmarks, we are going to measure our reaction times. And since it's a falling object, it should be falling 1 meter per second after 0.1 seconds. At 0.12 seconds, it should have fallen 1.2 meters per second. And after 0.15 seconds, it should be at 1.5 meters per second. After 0.18 seconds, it should be at 1.8 meters per second. And after 2.2 seconds, it should be at 2 meters per second. And again, that's because the ruler is a falling object, which accelerates at 10 meters per second.
And also, we know using our 5 benchmarks that the average speed that the ruler will be falling at is 0.5 meters per second after 0.1 seconds, 0.6 meters per second after 1.2 seconds, 0.75 meters per second after 0.15 seconds, 0.9 meters per second after 0.18 seconds, and 1 meter per second after 0.2 seconds.
Okay, based upon the information that my correspondents have already told our viewers, after 0.1 seconds, using the formula distance equals average speed times time, the ruler will have fallen 0.05 meters, which is equal to 5 centimeters. Again, this is through the formula distance equals average speed times time. So 0.5 meters per second times 0.1 second is 0.05 meters. After 0.12 seconds, the ruler will have fallen 0.072 meters, or 7.2 centimeters. After 0.15 seconds, the ruler will have fallen 0.1125 meters, or 11.25 centimeters. After 0.18 seconds, the ruler will have fallen 0.162 meters, or 16.2 centimeters. After 0.2 seconds, our last benchmark, the ruler will have fallen 0.20 meters, which is equal to 20 centimeters. We can now plot a graph of distance as a function of time, from the time 0, our first interval or benchmark, to the time 0.2 seconds, which is our last benchmark.
Alright, based on the numbers we've just given you, this is a graph of distance in centimeters versus time that the ruler will have traveled at our 5 benchmarks of 0.1, 0.15, 0.18, and 0.2 seconds.
Okay, now we will calculate Laura's reaction time just based on this ruler. Okay, I'm going to hold the ruler up. She's going to put her fingers at 0. I'm not going to tell her when I'm going to drop the ruler. I'm going to let the ruler fall. It's going to accelerate downwards at 10 meters per second squared, and she's going to grab the ruler as fast as she can. And we're going to read off the time, or read off the distance that the ruler has fallen in centimeters. We're going to do 10 trials, calculate the average, and then we're going to calculate her reaction time using the graph we talked about earlier and the formula. Okay.
Okay.
So trial number 1. 36 centimeters. You are very slow.
How was it?
Trial number 2. 34 centimeters. Number 3. 26. Number 4. 29. 5. 16. 26. 24. She completely missed the ruler. Let's try again. 21. 4. And the last trial, 28. 28 centimeters.
The ruler fell was 24.4 centimeters, or 0.244 meters. And so we plotted that onto our graph, and we got that the approximate time for her reaction time was 0.23 seconds.
Okay, and we can also use this data and calculate the reaction time of Laura more specifically. So it's more than just an approximation. So using the formula, D equals D initial plus V initial plus 1/2 AT squared, we can see that the initial distance that the ruler fell is obviously 0 meters. The initial velocity of the ruler is obviously 0 meters per second. And we know that acceleration is 9.81 meters per second squared. So with D initial and V initial being 0, we have the equation D equals 1/2 AT squared, where 2D equals AT squared, T squared equals 2D over A, so T will equal the square root of 2D over A. So now we will plug in our information. We know that T is equal to the square root of 2 times the average distance that the ruler fell when Laura attempted to grab it at 0.244 meters. And this will all be over acceleration of a falling object, which is 9.81 meters per second squared. So plugging this into our calculator, we find out that Laura's average reaction time is 0.223 seconds, which is extremely close to the approximation based on our graph of 0.23 seconds.
So, average swimmer leaving the blocks at the Olympics, their time was 0.6 to 0.7 seconds, and basically, I used to be a swimmer, and my reaction time was right in the middle of the average finger reaction time, which was
0.223, and the average finger reaction time is actually 0.2 to 0.25 seconds, so 0.223 is right in the middle of that.
So maybe that suggests that I could be an average Olympic swimmer at the Olympics. What do you think about that?
Maybe.
I think I could. This video was brought to you by Galileo and his concept of acceleration, and demonstrated by Laura,
Shane.
and Eric.